In this video, we're going to continue our discussion of multiple degree of freedom systems and finish up Chapter 8. Here we're going to discuss forced vibrations of undamped 2 degree of freedom systems. So the general form for a forced 2 degree of freedom system is shown here. We've got our mass matrix multiplied by our vector of accelerations plus our stiffness matrix multiplied by our vector of coordinates is equal to F1 of t, F2 of t, our vector of our forces. So the solution to this general form of the equations of motion is beyond the scope of this course. However, we can limit ourselves to considering forced functions, F1 of t and F2 of t, as being harmonic, in phase, and at the same frequency. So then these equations can simplify to the expressions here, where instead of generally F1 and F2 of t, we've got amplitudes F1 and F2 multiplied by sine omega t plus phi. So if the forces are harmonic, in phase, and at the same frequency as each other. Or we can write this in a more compact form. So with these equations of motion, we can look for solutions of the form x is equal to a sine omega t plus phi. So these equations of motion then become the expression here. We can cancel out our sine omega t plus phi, and this has to be valid at all times t, so we have k minus omega squared m times a is equal to f. Or we can call this za is equal to f, where z is defined as k minus omega squared m, which you can see here. Now, because the right-hand side of this equation is not zero, a unique solution for the amplitudes of vibration can be found. So A is equal to Z inverse F. So because our right-hand side was not zero, we don't need to have our determinant equals 0, so now we can actually find an inverse of this matrix and solve for A uniquely. So this is valid provided that determinant of Z is not equal to 0. So since Z is a 2 by 2 matrix, its inverse is given as this. So combining this with equation 8.36, we can see the solution for A1, A2. With the components of Z given as the essentially k minus m omega squareds. Now we saw in Chapter 4 how an undamped system can experience excessive vibrations if it is forced near its natural frequency. So this was the dynamic response of a forced, an undamped system. So if it's forced near its natural frequency, where omega over p is equal to 1, then we can get these excessive vibrations. Now, if we have to operate at this frequency, we can reduce the amplitude by increasing the mass, changing the spring stiffness, or adding damping. But there is another option, and we're going to discuss the idea of a vibration absorber. So a vibration absorber, which is shown here, can be added to the system to reduce the vibration amplitude at a specific operating frequency. So basically, if we have our original system, a vibration absorber is just an additional spring and mass system that's added to our original system. So it's simply another spring and mass that's added to the original system. So but we try to select the parameters M2 and K2 to minimize the vibration of the original system. So we can draw a free body diagram, mass acceleration diagram of this 2 degree of freedom combined system. And we can use Newton's laws to write our equations of motion, which we get here. So in matrix form, we have the equations of motion for this system as shown here. So this is just a special case of the forced 2 degree of freedom system with our F2 is equal to 0. as the F naught is only applied on our original system. So we only have this here. And on the vibration absorber part, there's no external force applied. So again, we look for solutions of the form x is equal to x sine omega t. So the equations of motion then become this here, where we can, this has to hold for all time t, so we can cancel out sine omega t. And we get this expression here, which can be arranged into this matrix multiplied by our vector x1, x2, which is equal to F naught and F, our force vector. Now, to solve for the steady state amplitudes, we see that from the second equation of this, x2 is equal to k2 over k2 minus m2 omega squared times x1. So this makes the first equation given by this expression here. So x1 can be solved as we can see here. And substituting this, if we call this first expression from our first equation, call that star, and we substitute x1 into star, we get this equation here for x2. So we could have found the same result from 8.36 directly, because we had 8.36 was that x was our a is equal to z inverse f. Now, if we want to non-dimensionalize the results, we can divide the top and bottom by k1, k2. And so that this is the form of our x1 and x2 now. And then define F naught over k as the static deflection of the original system, so delta static of the original system. P11 squared, which is k1 over m1, is the natural frequency of the original system. P22 squared, which is k2 over m2, is the natural frequency of the vibration absorber in isolation. And mu is m2 over m1, which we call the mass ratio. So defining all of these terms, we can get these expressions here in their non-dimensional form. So you can see that the amplitudes x1 and x2 depend on our forcing frequency omega, and they depend on the natural frequency of the original system, which was P11, and the natural frequency of the vibration absorber in isolation, which was P22, and they depend on the mass ratio between the original system and the vibration absorber, this mu, as well as the delta static. So from in order to get these equations, we made use of the fact that k2 over m1, or k2 over k1 is equal to p22 squared m2 over p11 squared m1, which is equal to mu times p22 over p11 all squared. Now p11 and p22 are the natural frequencies of the original system and the vibration absorber in isolation. So it's important to note that they are not the natural frequencies of the combined system. We're going to discuss those shortly. So they're the natural frequencies of the original and the vibration absorber system in isolation. Okay, so let's look at our first equation here. So we can see that the amplitude of vibration of the original mass is 0 if the natural frequency of vibration of the vibration absorber is equal to the forcing frequency. So if P22 is equal to omega, then the amplitude of x1 is going to go to 0 because of this term on the top here. So this is the ultimate goal of the vibration absorber. We want to be able to find these parameters so that the amplitude of vibration of the original system is equal to 0. So if this is the case, then the amplitude of the vibration absorber itself is not 0, but is given by the expression for x2. So if this term goes to 0, then our x2 is equal to minus delta static over mu, p22 over p11 squared, which reduces to minus f naught over k2. So this is the amplitude of the absorber is the same as that as what would result if the disturbing force F0 was applied statically to the absorber in isolation. The negative sign indicates that the absorber mass moves out of phase with the disturbing force. So let's look at this here. So this is our original system with the vibration absorber attached. This is what happens when the vibration absorber is at its lowest position here, and when the vibration absorber is at its highest position here. So you can see that it's moving out of phase with the force. So when force is going up, vibration absorber is going down. When force is going down, vibration absorber is going up. So the absorber mass moves out of phase with the applied force, and the original mass is always in equilibrium and does not move, which again was the goal of adding the vibration absorber. So the absorber is allowed to move, but the original system doesn't move. So since omega is equal to P22, which is the square root of K2 over M2, to obtain P22, we have to choose a large K2 and a large M2, or a small K2 and a small M2. In the first case, the mass might be too large to be practical, and in the second case, the resulting isolation, the isolator vibration amplitude might also be large enough to cause problems. So practical choices in the design of a vibration absorber will require trade-offs between these two conditions. We also have to consider the response of the combined system. So the addition of the vibration absorber will result in zero amplitude of the original system at its forcing frequency omega. This forcing frequency omega is not a natural frequency of the combined system because we would expect the response at a natural frequency to tend towards infinity. So we can find the natural frequencies of the combined system by setting the denominator of 8.42 a and b to 0 because that makes the amplitude grow to infinity. So this is one of the denominators, which we can call 8.44, and we'll set that equal to 0. So let's expand this and substitute p equals omega, because basically what we're saying here is when the system is forced at one of its natural frequencies, the denominator will go to 0. And so to be able to find the natural frequencies, that when omega makes that equal to 0, those will be our natural frequencies. So we'll expand this out and we can cancel out some of the terms, and we get this expression here. So this is a quadratic equation for p over p22 squared. You can see that p over p22 to the fourth and p over p22 squared here. So the quadratic equation depends on p11, p22, and mu. P11 can't be adjusted because it's the natural frequency of the original system. P22 is usually selected to be the same as the forcing frequency. But the quantity mu, which was our mass ratio, can be adjusted for the vibration absorber. So let's consider a situation where the original system was operating at resonance. So omega is equal to P11 is equal to P22. So our equation reduces to what is shown here. So the effective altering mu for this equation is shown in these images here. So on the left-hand side is, so these figures are x1 over delta static, and these figures are x2 over delta static. So with a mass ratio of mu is equal to 0.05, you can see that we have now separated the natural frequencies by a small amount here. So these are the natural frequencies of the combined system. And with a larger mass ratio, x is equal to 1, you can see that we've separated those natural frequencies by a much larger amount in this case. So the natural frequencies from the previous slide are shown in an alternate format here. So this is mu, in this direction, and this is our P over P22. So as mu gets larger, the natural frequencies get further away from the original natural frequency. And these results, remember, are for a system that was operating originally at resonance. The same principles do apply for other forcing frequencies. But if originally we were forcing it at resonance, now we've separated our natural frequencies of our combined system. And for a small mass ratio, they're separated just a little bit. And for as mu gets bigger, we can see that these natural frequencies separate more. So while this is very effective at omega over P22 is equal to 1, if the excitation frequency moves, we are very quickly at another resonance. So to broaden the effectiveness of the system, we can also add damping. And in the example of buildings, we often need to guard against both ground-borne and wind excitation, so we need more flexibility in the system. The analysis of a damped vibration absorber is beyond the scope of this course, but it's important to understand that this is a very useful way to increase the effectiveness of a vibration absorber type system. And an example of a damped vibration absorber is called a tuned mass damper. And one of the biggest and kind of most famous examples of a tuned mass damper is in the Taipei 101 tower in Taipei, and it's 660 metric tons. It's essentially a large pendulum that hangs in the top of the building, and it's open and can be seen, and is not only a functional piece of the building, but it's also an aesthetic and interesting sort of showpiece of the building as well.